Here we go. Another fabulous day here in Calculus 3, folks. We're going to do optimization. That means finding maxes and mins with word problems. So let's find a max volume. Rectangular box is resting on the XY plane with one vertex at the origin. Ooh, okay. And his other vertex lies in this plane. Let's graph this plane. So if you find the X, Y, and Z intercepts of this plane and graph the portion here in the first octant, set Y, Z as simultaneously equal to 0, I get X equals 4 for an X intercept. If I set X and Z equal to 0, I get Y equals 6 for the Y intercept, and then setting X and Y, I get an 8. And so the portion of the plane here in the first octant is there. Now, where is this rectangular box? Well, he's behind the plane. If you can imagine, I've got a box down there resting flat on the XY plane, and it's kind of hard to draw 3D. This point right here, this opposite vertex from the origin, is in this plane here. That's what's stopping it from being able to grow, if you will. That plane is sort of like a barrier for that poor box. So how big can the box get? Like, how we want to maximize the volume. So we're going to try to find the dimensions of the box that maximizes the volume of that little red box. Okay, fine. How do you do that? No. This is a little bit tricky of a problem because a lot of students, the minute they see this plane equation, they start doing calculus on that. And that's not the equation that you're going to do calculus on. So that plane equation is what we call the constraint. That's just constraining your box from being able to grow to the biggest max he could possibly get. And you don't do any calculus on your constraint. Well, where are we going to do the calculus then? Well, we need to maximize volume because that's what they want. So the quantity to be maximized needs to be a volume equation. So volume of a box is X, Y, Z. So X, Y, Z, width, length, height are the dimensions of the box. Okay. So you're going to do calculus on this. Now, a little bit of a problem is arising right now. This volume function happens to be a function of 3 variables. Uh-oh. Why is that a problem? Because when we learned the D-test, and we just spent this last hour doing lots of stuff on functions of 2 variables, not 3. So now what? We need to reduce the volume to a function of 2 variables. Well, how do we do that? You just erase the Z and pretend it doesn't exist so it could be a function of X and Y? No. You're going to use the constraint to do it. So what do I mean by using the constraint? You're going to take your constraint equation and you're going to solve it for Z, and then you're going to substitute that Z expression into your volume function so that he can have only X's and Y's in it. And then we can do all the work. So when I solve this plane equation for Z, I get 1/3 times the quantity 24 minus 6x minus 4y. That's pretty gross. I know. So then your volume equation, if you're now going to just have it be a function of x's and y's, is x times y times z, but you're going to plug in this 1/3 24 minus 6x minus 4y. That's the function you're going to do calculus on. Oh man, that's going to kind of suck. Yeah. So what I'm going to do is I'm going to leave the 1/3 out in front because I hate fractions. And I'm going to distribute the xy over the parentheses. So my volume function after distributing the xy is 1/3 times 24xy minus 6x squared y minus 4xy squared. Oh my God. Yeah. And the partials. What are the partials? Vx and vy. Here we go. Vx is 1/3 times the quantity 24y minus 12xy minus 4y squared, right? That's x. And then the Vy is 1/3, 24x minus 6x squared minus 8xy. Fine. You're going to simultaneously set both of these equal to 0. Those are definitely non-linear equations. So, oh my goodness, this is going to be pretty gross. We're going to cut it down and make it easier. You'll see in a moment by factoring and applying the ZPP. Oh gosh, I keep saying that over and over, don't I? Oh, I hope I'm not sounding too redundant. So the Vx, what I want you to notice is that the three terms that are in there, they do have a common factor. So let's pull out, and I know I could pull out 4y. I'm just going to pull out a y only, if you don't mind. So then I have 24 minus 12x minus 4y. That's equal to 0. And if I factor Vy in a similar way, noticing that x is common to all three terms, my Vy will look like this: 1/3 x, 24 minus 6x minus 8y. And that's got to equal 0. Okay, is this getting me somewhere? Thanks for asking. Yes, it is. Now, here's what I want you to notice. If you apply the ZPP to Vx, I hope you could see that y equals 0 is definitely going to make Vx go to 0. Okay, fine. If you apply the ZPP to Vy, I hope you can see that x equals 0 is going to make Vy go to 0. So I claim that 0, 0 is indeed a critical point. Okay, but for this problem, because of the nature of the real life problem, I'm going to throw out this critical point and not deal with it or do the d-test on it or anything. Why do you think that? Why can I make the case that for this cute little box, I'm going to throw out 0, 0 as a critical point? Anybody want to gander a guess? All right, I'll just tell you. Well, because x and y were the width and the length of the box, it isn't a very interesting box if your width and length are 0, okay? I don't even think it qualifies as being a box anymore. So that is not a very interesting critical point for us. We don't want a box that's like a dot. So we're going to ignore this critical point because it's a real life problem. Now, folks, for future reference, don't think that every time you get a 0, 0 as a critical point, you can throw it out and ignore it. No, that's not the case. In fact, this last hour we just spent where 0, 0, it was a very key critical point, and you want to acknowledge it. But this, because of the nature of the real life problem here, where we don't want boxes that have 0 widths and lengths, we're going to just ignore it. So then what? Well, if you look at the rest of the factor here, if we kind of throw these guys out, what's left? I don't care about the 1/3 either, because the 1/3 can never be equal to 0. Let's just look at that. This is the system that I'm going to try to solve right now, okay? That's the system I'm going to do business with. Yeah. And folks, this is a linear system of equations, so it's not so hard to solve. I'm going to rewrite them because I like it when my variables are on one side and my constants are on the other because it looks prettier. Yeah, that's just how I roll. And then you can use the process of elimination or substitution because you learned from algebra how to deal with systems that are linear to solve. It's up to you. Like if I multiply this second equation on both sides by -2 and then rewrite the system. So here's equation 1. Here's equation 2 after multiplying both sides by -2. If I add these two equations together, I'll eliminate the x. Cool. And then what? I'll have -12y equals -24. And then solving for y, y is 2. Cool. And then what? Well, go get your x. Well, how do I get x? Well, you can substitute it into either one of your two original equations. How about this if I substitute it into the 6x plus 8y? That one's nice. 6x plus 8y has to be 24. And so then what? 6x has to equal 24 minus 16. 6x has to equal 8. X is equal to 8, 6. which reduces to 4/3. Okay, so what do I have right now? I have two of the dimensions, but I have a critical point, 4/3 too. That is a critical point. Yay. And now you can go do the D test and prove to me that that does indeed maximize your volume function. So if you get D, which is Vxx Vyy minus Vxy squared, Vxx turns out to be negative 4y. You can check me on that. Vyy is negative 8/3 x. And by the way, when you go get your Vxx's and Vxy, you do have to go go back to your original here. Okay, not the reduced version. Be careful. So then your Vxy is pretty gross. It's 1/3 24 minus 12x minus 8y. And you're going to want to square that. That looks horrible. When you evaluate D at this critical point, 4/3 2, I'll just cut to it. I get something positive, 64/3, which is good. And then Vxx evaluated at 4/3 2 is a negative number. So I do indeed have a rel max, which is what I wanted. I wanted to maximize my volume. So now go give the dimensions. So you have that x is 4/3, y is 2. You need to go get your z. So how do you get your z? Remember that z had to be fulfilling on the constraint. So remember when we solved for z way back here? You can plug the point 4/3 2 into this plane equation to get your z. And it turns out your z, or the height of your box, is 8/3. And so your final answer is your volume is going to be 4/3 by 2 by 8/3. And that ends up being 64/9 cubic units. And that's your max volume. Okay, so these are the dimensions that will maximize your box, and 64/9 is the value of that maximum. Pretty cool. The calculus can be used to do that. If you're still here, congratulations. Let me do a profit function and max profit, and we'll be done for the day. Woo, we're going. So I love this problem because, you know, I used to teach business calculus many years ago, and I like to bring in some economic stuff in here. You know, you guys should know a little bit of econ. Maximizing profit. So they're telling you this profit by a company produces X units of product A and Y units of another product they sell, product B. Cool. And they're giving you a profit function. Cool. And they want you to find the production level for the products that will maximize their profit. Fine. And then give the actual profit that is maximum. Great. So what I'm going to do is I'm going to find the partials very quickly here. Partial of P with respect to X is 8 minus that 0.001 times the quantity 2x plus y. The PY is 10 minus 0.001 times x plus 2y. Yep. And you're going to set them both equal to 0 simultaneously. And folks, good news, these are both linear equations. So this is a linear system. Now, I don't like the decimals. I mean, you can do this without dealing with decimals. That's fine. But what I'm going to do is I'm going to multiply both sides of the equation for both equations by a 1,000, because I can, so that my px is going to look like, after I multiply both sides by 1,000, 8,000 minus, this thing goes to 1. So it's just going to be the quantity 2x plus y, and 0 times anything is 0. And then when you multiply the partial with respect to y by 1,000, you get that. Now you may think that, well, that's so what? But now when I rewrite the system, so the variables are on one side and the constants are on the other, just to look more traditional. That's how you looked at it when you took algebra, right? And then you can solve this either using substitution or, you know, elimination. your choice. If I multiply both sides of equation 1 by -2, say, and then add it to equation 1, I can eliminate, don't forget to distribute that -2. That's a big no if you forget. When you add these two equations together and I get rid of the x, cool. I get -3y is equal to, good Lord, -12,000. Yeah. And then divide both sides by -3, y reduces to 4,000. Back substitute this into either one of the two original equations to get x. Okay, doesn't matter which one. Okay, like how about if I substitute it into, I don't know, this one right here, x plus 2y is equal to 10,000. So x plus 2 times y is equal to 10,000. This right here is 8,000. And so if I subtract 8,000 from both sides, I get 2,000 for x. Now, what does that mean? So this business, basically, it's looking like their critical point is when they're selling 2,000 units of product A and 4,000 units of product B. Now, prove that's a max, okay? So I would want you to go, get your D, do your PXX times PYY minus PXY squared. And when you do that, what is your PXX? I get minus 0.001 times 2. And then your PYY looks like it's minus 0.001 times 2. Minus PXY, minus 0.001 squared. If you evaluate the critical point at this D quantity, you should get something positive, and then your PXX is a constant and it's already negative. So this definitely gives you a real max for your profit. Yay! And that's what you wanted. And now go figure out your actual max profit. How much money are you going to make for the company? Well, you're going to substitute your critical point, 2,000, 4,000, into your profit function. So you're going to go, all right, 8 times 2,000 plus 10 times 4,000 minus 0.001 times that. What was that thing? Is that right? Yeah, x squared plus x. This is sort of the pain in the butt part. Like, oh man, are you kidding? No, 2,000 squared plus 2,000 times 4,000 plus 4,000 squared minus 10,000. Okay, it turns out that 18,000, and this is in dollars. So $18,000 of profit at that critical point. Not bad. And there's a word problem. And you'll have something similar in your quiz. You'll be fine. It's easy.